So the dot product. When you deal with scalar, you have four operators: plus, minus, multiplication, and division. When you deal with vectors, the multiplication operator split into two. There are actually two different ones. There's the dot product and the cross product. So we'll investigate the dot product first. The definition of a dot product is if you have one vector A dot another vector B, it is equal to the magnitude of A times the magnitude of B times the cosine of the angle between those two vectors. So if vector A is like this, vector B is like that, theta is the angle between those two vectors, and then the dot product between those two vectors is the magnitude of the first one times the magnitude of the second one times the cosine of the angle between those two vectors. This is a nice definition if you're dealing with vectors given to you in terms of magnitude and angle. Then all you have to do is, say, align one vector along the x-axis so that the angle is 0, and then you draw the other vector such that theta starts from the b vector or the x-axis counterclockwise up to the first vector. You will also notice that even though we are starting with two vectors, we end up with three scalars: magnitude of A, magnitude of B, cosine theta. So dot product is a scalar. We will see that it's very different from a cross product, which gives us a vector back. So that's the main difference between dot product and cross product. We have two interesting cases for dot product. First interesting case is when vector A and vector B are collinear. So they are parallel to each other and pointing in the same direction. If you have such a case, then the angle between A and B is 0. And since you have to take the cosine of the angle, cosine of 0 is 1. Therefore, A dot B is nothing else than magnitude of A times magnitude of B times cosine of 0, which is 1. So it's just the product of those two magnitudes. Now if you start increasing the angle between the two, to such a value that the angle end up being exactly 90 degrees, or pi over 2, then in this case cosine of pi over 2 is 0. Therefore dot product between A and B is magnitude of A times magnitude of B times cosine of pi over 2, which is 0. So the whole dot product is 0. And then as you keep increasing the angle, then the cosine will become negative, and it will go again towards its maximum value in magnitude, which is 1. So really the dot product goes from A times B, then it decreases as you increase the angle, up to its minimum value when theta is equal to pi over 2, which is 0. And as you keep increasing theta again, the dot product increases again its value, but this time towards the negative direction, or the negative, such that the other extreme value is when theta is pi, cosine of pi is minus 1, so you end up with A dot B is equal to minus magnitude of A times magnitude of B. So really the two cases, interesting cases that you want to keep in mind is when you're dealing with two vectors which are collinear, then the dot product is just the product of the two magnitude. And when those two vectors happens to be perpendicular to each other, then the dot product is 0. So if A is parallel to B, A dot B is plus or minus AB. And when those two vectors are perpendicular to each other, A dot B is equal to 0. Keep those in mind because those two cases will come back with the cross product, but the result will be opposite. Okay, we have the same rules as when you add two vectors with scalars or multiply them with scalars. You can do the same thing with the dot product. So the first is the commutativity. If you have a scalar which multiplies the dot product, then you can distribute your scalar either to the first vector or to the second vector. Doesn't matter. Both are equivalent. Similarly, if you have a scalar multiplying, now if you have a vector dotting the sum of two vectors, then you can use the associativity rule, which is the first vector dot the second vector plus the first vector dot the third vector. So you end up with A dot B plus A dot C. Okay, so we've just seen the definition of a dot product in the case where you're being given vectors in magnitude and angle. Now, if you're being given those two vectors in component notation, how are you going to deal with it? So let's see how that goes. Let's imagine we're working in 3D. We can write each vector in component notation. So vector A would be AXI plus AYJ plus AZK. And let's say vector B is BXI plus BYJ plus BZK. If you want to take the dot product between those two vectors, all you have to do is take every term and dot it with every other terms. So you will start with the first term, take the dot product of this term times the first component of the other vector. Then you're going to add the dot product of the first term of A dot the second vector of B. And then you're going to add the dot product between the first vector of the first component of A dot the last component of B. And then you're going to jump to the second component of A, dotting the first one, the second one, the third one, and so on. The last one dotting the first one, second one, third one. So if you're working in 3D, you should have 9 terms. And if you're working in 2D, you should have 4 terms. So let's write down every term explicitly. So first term, AX I dot BXI. Now remember those commute, so I'm going to put all the scalars together. AX, BX. Those are two scalars. So I end up, with another scalar, and then I dot I. Then the first term with the second term. So AX times BY multiplied by A dot J. And then AX BZ I dot K. Then let's jump to the second term. AY times BX I dot J dot I. But we've just seen that vectors commute under the dot product, so A dot B is the same as B dot A, so whether you write J dot I or I dot J shouldn't matter. Second term AY BY J dot J. Last term AY BZ J dot K. And then the last three AZBX K dot I AZBY K dot J azbz k dot k. So let's look at every term. I dot I. This is the case where you have two vectors which are parallel to each other. Therefore, I dot I is equal to magnitude of I times magnitude of I times the cosine between those two i's, which is 0. So cosine of 0 is 1. Since the magnitude of a unit vector is 1, that's just 1. And that's exactly the same thing for j dot j and k dot k. So this term, and this term are equal to 1. Let's look at the other term, I dot j. We will end up with magnitude of I times magnitude of j times the cosine between those two unit vectors. Since we're dealing with a orthonormal system, the x-axis is perpendicular to the j-axis, which is perpendicular to the z-axis. Therefore, the angle between every axis is 90 degrees. Cosine of 90 is 0. Therefore, I dot j has to be 0. Similarly, I dot k, j dot I, j dot k, etc., they're all 0. Therefore, all the other terms, I dot j, I dot k, j dot I, j dot k, k dot I, k dot j, are all equal to 0. So really only 3 terms survives, which are ax bx times 1, which is the I dot I, ay by times 1, which is j dot j, and azbz times 1, which was k dot k. Sure enough, scalar, 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 the dot product is a scalar. Okay, so in general, when you take a dot product of two vectors written in component notation, all you have to do is multiply every terms that are alike. So multiply all the i's together, all the cross term will cancel. Will go to 0. So multiply all the i's together, all the j together, all the k's together. Now let's look at a particular relationship that will be useful one more time during the semester, and it will come back in C271. We know how to write a vector, let's say u, and decompose it into two vectors along, say, your xy coordinate system. So u can be decomposed as ux plus uy. Or we used to write ux as magnitude of ux times unit vector I. Vector uy is magnitude ui times unit vector j. So u was uxi plus uij. That was the component notation. Let's use the exact same idea, but this time, instead of choosing our coordinate system to project our vector and decompose it, we're going to pick any line. So let's imagine we have line L. Let's define a unit vector along that line. Let's call it E. And then we have our favorite vector u. And what we would like to do is decompose that vector u into two vectors such that one component is parallel to L. We'll call that up. And the other component is going to be perpendicular to that line L. Let's call that un. So really there is no difference. Before we used to have x in this direction, y in this direction. So now we're just shifting our coordinate system, and we align our x coordinate with the line that's given to us. So we're going to do the same thing. Let's look at our little triangle. We have a right triangle. We can define the angle between vector u and vector up, and the angle between those two vectors is theta. So by geometry, we know that the magnitude up is nothing else than the magnitude u times the cosine of the angle. So by using Pythagoras theorem, magnitude of up is equal to magnitude of u times the cosine of the angle, theta. So we know how to do that. Now we would like also to take the dot product between our unit vector E, which is a line along L, or a line along UP, and dot it with our vector U. Let's use the definition that we've seen at the beginning. A dot B is equal to magnitude of A times magnitude of B times cosine between those two vectors. The angle between vector U and unit vector E is the same as the angle between vector UP and vector U. So U dot E is equal to magnitude of vector unit vector E times magnitude of vector U times the cosine of the angle between those two vectors, which is cosine theta. Now we're dealing with the unit vector here, so by definition we know that unit vector has length 1. Therefore E dot U is equal to magnitude of U cosine theta. Now look, U cosine theta, U cosine theta. So we have A is equal to B, C is equal to B, therefore A must be equal to C. So we can write that the magnitude of UP is equal to unit vector E dot vector U. Now we can go back to the definition of vector. We can write the vector UP in terms of its unit vector. So vector UP is in general magnitude UP times its unit vector. And the unit vector EUP is exactly the same as the unit vector E, because those two vectors are parallel to each other. So really I can rewrite UP vector as magnitude UP times our unit vector E. Now I can plug what I've derived here for the magnitude of UP and put it right there, and I end up with vector UP is equal to unit vector E dot vector U times unit vector E. So if you have vector U and you would like to find the component of U, which is a line with the line L whose unit vector is E, all I have to do is take the dot product between unit vector E and the vector U and multiply it again by vector E. You will notice that here there is nothing. That's okay, because unit vector E dot vector U is a scalar, so this is a scalar, so you don't need to specify anything. Multiplication is just multiplication. And then since we know that U is equal to UP plus UN, you start with U. We just calculated UP. You can deduce UN such that UN is equal to vector U minus the one we just derived, UP, or UN is equal to vector U minus E dot U times unit vector E again.